Okay, works. Okay, so I'm a postdoc working in Samuel Kaski's group at Aalto University and is also affiliated with the University of Manchester. So this work is a recent work with our collaborator Louis, who was at Aalto University, but now he's an assistant professor in Rennes, I think. So yeah, let's get started. Yeah, okay. Let's continue with the introduction. So the setting that we're talking about is of basically inference from data. So let's say you have some data Y, ops, which can be denoted by some empirical distribution Qn. And you also have, let's say, some parametric model, m theta, with parameters theta. And what you want to do is, given these data set, you want to estimate theta such that your data distribution is closest to your model in some sense. And now if you take this sense to be, let's say, the Kullback library divergence, then you get the maximum likelihood estimate, where you maximize the probability distribution of the data given theta. Or if you could do Bayesian inference, where you sample, wait, sorry, I didn't mean to do that either.
Left to right, the other way, left to right.
Ah, okay.
Right. Yeah. Yep.
It went quite far back for some reason. Okay, and we're back. So, and then, or you could do Bayesian inference. You can, which also relies on the likelihood function. Now, the problem is that for many models in especially physical sciences and engineering, the likelihood function is intractable, which means that it's not available, definitely not available in closed form, and cannot even be evaluated numerically or approximated in reasonable computation time. Which means that these maximum likelihood and Bayesian inference methods, the classical standard inference techniques, are not applicable in this scenario. What could cause a model to have an intractable likelihood? Well, the model could be simply too complex, and by which I mean, think of a model as like a simulator program, like a computer program, which has a bunch of different steps that you need to do, like maybe solve a lot of differential equations or models of how the universe is simulated and so on, where you cannot even write down what the likelihood function is. Or it could be that the variables that are important for the likelihood description, they are unobserved. So let's say hidden variables or latent variables in the model, which where the observed data is some complicated nonlinear transformation of those hidden variables. Okay, or a naive reason could be that it's just a new model. It happens in engineering, people make models, but that try to capture some real world phenomena, but it's the likelihood function needs some work in order to be derived. Anyway, so these kind of models are called, people call them simulators or implicit models or generative models in general. One feature that they all have in common is that even though their likelihood function is intractable, but they are easy to simulate from. So if you just put in some values of the parameters, you can generate some fake data out of it, which might not make sense, but at least the generative process is quite straightforward. Okay, so some examples of these kind of simulators in physical sciences and engineering. So it started off in the last 2 decades, I think, in population genetics. So that paper is like considered to be the first paper in this field. And then so in the beginning, there were a lot of these domain experts of population genetics and ecology and evolution that were working on these methods because they had these models that they needed to infer. And then slowly, these methods became a bit more popular. And then you can see recently a lot of different domains have picked it up, both sciences and engineering, and even economics these days. So the way that these people fit their models is by using something called likelihood-free inference methods. So we cannot do some likelihood-based, so we need to do something likelihood-free. And ABC, which is approximate Bayesian computation, that's one way of doing it. It's, I think, the most popular one, and that's the one that that 1999 paper was talking about. Okay, so that's the main topic of this talk.
Is this a good place to ask a question?
Yeah,
Yeah, if I can ask a question, do you know what those fields that only recently picked it up, what they were doing prior to?
This way, right?
No.
Ah, sorry.
Yes.
Slightly counterintuitive because I want to go back. Anyway, I can only tell you about this field because
All right.
yeah, that's me. So what people were doing, so they have these point process based models where you first generate, let's say, marked point from, let's say, some Poisson process. And then you transform them using some Fourier kernel, some very complicated nonlinear information. And that's the data that you observe. Okay. Now, what people were usually doing is kind of breaking down this process into like boxes. So first, they would, let's say, estimate these hidden variables by some fancy estimation techniques. Then these models also are clustering based usually. So then they would take these, let's say, point process, like these points, basically, cannot write it down. And then they cluster them. So that's another box. And then they would fit it. So it's very hacky, ad hoc engineering way of doing things, which meant that every model that you come up with, it's up to you to how to figure out how to fit that model. So you cannot use any standard statistical techniques. So now I don't know what the other ones were doing it. Actually, this is what I wanted to talk about. That in these kind of models are becoming prevalent only in the last decade, a couple of decades. And there's a reason for that is because, first of all, the machines are becoming more and more powerful, which means that you can make more accurate descriptions of real world, even though it takes more time to do all the computation, but people have nice GPUs and supercomputers to do that. And also the statistical techniques are evolving to handle a lot of data. So the limitation that, let's say, maybe 2 decades ago, people would have in sciences or engineering, that, oh, you could write a more complicated model, but there's no way of running it or evaluating it. So that limitation is gone. That means more simulators coming up. That means we need more of these methods. All right.
No.
Hopefully by the end of this talk, I'll get that. Okay, so let's go to ABC. So ABC is, as I said, a likelihood-free inference method that allows you to sample from the approximate posterior of your model, given that the model is easy to simulate from, which means that the forward simulations should be straightforward. I mean, if you cannot even do that, then there's no hope. Okay, so a simple rejection ABC algorithm goes in the following manner. You sample from the prior. Okay, you take one sample, and then you simulate data from your model. And then you compare some, usually the data is high dimensional, so you could not just compare the data sets themselves, but you compare some summary statistics of your observed data and your simulated data. And if they are small enough, like if they're close enough, and this closeness defined by this epsilon, then you accept that parameter sample as being a sample from the approximate posterior. And then if you repeat this process again, you get, let's say, n accepted samples. They form, IID samples from the approximate posterior. So here, rho is the distance between statistics. S is the summarizing function, and then epsilon is this tolerance threshold. So if you put epsilon to 0, then you would get back the standard Bayesian posterior. Of course, granted that you have sufficient statistics here. Okay, and yeah, it works with the finger also. So now the approximation in ABC arises from basically these two things that I just described. One, that you have epsilon, which is non-zero. So you are accepting samples which didn't exactly come from your data distribution. And the other one is that you're using a few statistics to do some dimensionality reduction of your data, which means that you're throwing away some information. I mean, you could use sufficient statistic, but in practice, it's usually not available. All right. So, and that's why it's approximately Bayesian. So the three ingredients that you need to implement an ABC algorithm is the distance metric, summary statistics, and the tolerance threshold. Okay, so now choosing epsilon is, now there are some papers that have worked on it, but in practice, what I've seen is people just use, let's say, a percentile of your simulated sample. So let's say you simulated 10,000 samples, and then you pick, let's say, the best 1% or 5% that yielded the smallest distance. And then those so epsilon becomes like 5% or 1%. So you define it in terms of percentile. That's a practical way. At least that way, you know how many samples, what is your simulation budget. Otherwise, if you keep on running till you get an accept, if you chose epsilon very small, the computation time increases. The acceptance rate goes down, basically. The next one is choosing the distance metric. Now, if you already have some statistics that you are computing distance of, people usually use Euclidean distance then, but you could also use some distances on the data sets themselves. If you have, let's say, a suitable kernel for it. So people have proposed the maximum mean discrepancy ABC and Wasserstein ABC. But I mean, in practice, the data dimension is quite high. So even people who, let's say, propose the MMD ABC, they ended up at least summarizing to some degree and then applying this method. Anyway, so these are the distance metric. Now, choosing the statistics, it's slightly non-trivial. Because now there's a trade-off between how much you want to summarize because you're throwing away a lot of information, but at the same time, you want the statistics to be as low dimensional as possible because you're computing distances, and then you don't want to compute distance in higher dimension. So there's this trade-off between information loss and curse of dimensionality. And to be honest, this is like there's no one solution for solving this problem, which is why we frame it as the fundamental unsolved problem in ABC, just a marketing technique. Yeah, so choosing summary statistics. So what happens in practice, which is, let's say, what I did for my radio communications work that I was doing, is that you need to handcraft manually these statistics. Because you also know, depending upon the field, depending upon the model, the data, some statistics might mean something. And you know that, okay, this parameter affects this thing. So, you construct statistics like that, which is quite time consuming and involves multiple trial and error. You try this statistic, didn't work, and then you do something else, and so on and so forth, till, you get something which works fairly well. And you have no idea of knowing how, well it is. So this finding the statistics takes up majority of the time of any, likelihood-free inference project, as at least it did for me. So domain knowledge is, of course, vital because you also, maybe you want to fit certain characteristics of the data or the model, right? So if you do it kind of automatically, then you lose this sense of, what am I exactly fitting? Okay, so now there are existing methods that try to handle this problem. So given a pool of candidate statistics, now again, this pool usually comes from domain expertise, but let's say you have a bunch of different statistics that you could use. Then you can apply some subset selection techniques. So they will try to find the best subset, which has approximately the same information that the full set has. Or you could do some projection techniques, which is you project this, let's say, higher dimensional space of statistics onto a lower dimensional and more informative space. Or the other one is regression adjustment. It's not exactly a subset selection technique, but I mean, it's just a conditional density estimation that you could use. This we'll talk about more later on. So what we recognized was that, I mean, the performance of these methods, they degrade when you have less amount of simulations that you can do from the model, which is basically you have less data. I mean, any model performs worse then. And when the model is misspecified. So when your true data distribution does not lie in your model family. So because the ABC still is trying to approximate the standard Bayesian posterior. And I mean, in this case, even the Bayesian posterior is erroneous, right? All right, this is the time for another round of questions before we go on to, let's say, more details of some ABC methods. Yes?
So is it possible to not use sufficient statistics, but just directly measure the distance of two samples, the sample observations?
Yes.
Could you repeat the question? I jumped.
Yes. So what Hudson is asking is, can we, instead of doing summarization, can we just compare the data points directly?
Yes.
Right. So yes, you could do that if you have, like, for example, you could do that with MMD, provided you have a good kernel for it. So now the problem moved from finding statistics to finding a good kernel, which is, I mean, it's probably equally hard. So it depends upon the data. I mean, if your data is, let's say, fairly low dimensional, I mean, you could use MMD, but you could even summarize it, and you would get reasonably well answers. But imagine, like hundreds of dimension time series, and you have multiple such time series, then, and that's one data point, then it becomes a bit difficult to, compare in such high dimensions. Yeah. All right. So now we'll take a look at these regression ABC methods a bit more in detail, and then show these two problems that we kind of recognized, how they affect this particular method. So what regression ABC does is, it basically does rejection ABC first. So let's say you do your rejection ABC, and then now you have accepted some theta i's and some corresponding statistics. So let's say n epsilon statistics you have accepted. And then you basically do some conditional density estimation. You try to estimate theta given S. And then you put, let's say, you assume that theta is some function of the statistics and some noise. And we want to estimate, let's say, the parameters of this regression model. Okay. And so you could use a linear regression here. You could use a neural network or some other type of regression that you fit on this data. So what is happening here is, graphically, let's say you have only one statistic and you have only one parameter. And this is, let's say, the prior range that you sampled in. Okay. And this is the...
No, that's right. That's right.
Okay. And this is, let's say, the range of statistics that those parameters generated. Okay. So these are, let's say, some of the points here. Now you fit a model to this, and then you condition on the observed statistic that you got, okay, which basically moves these points onto the SOBS vertical line. And so you go from something which is slightly more, broad posterior to something more concentrated because of this adjustment. It's called regression adjustment ABC, which is all well and good. And in practice, it actually works very nicely, provided that your model is not misspecified. Or in this case, because we're talking about statistics, provided that the statistics do not mismatch between the observation and the simulation. So it's the same figure here. Now, what I just did was I put the observed statistic outside. So now the model for any value of theta cannot produce any statistic which your data gave. Maybe the data has some outliers, noise, whatever. Then what this method does is it pushes everything onto exactly this line, which means that your posterior even might go beyond your prior range. Okay, which is of course highly undesirable. And so this is a graphical representation, and this is, let's say, for one particular model. This is one parameter of that model. This is the well-specified case. You can see the true value is very close to, let's say, the posterior is quite narrow. And then when the model is slightly misspecified, then now here I'm constraining the posterior samples to be in some range. Everything is kind of pushed onto, let's say, one of the prior boundaries. So, I mean, if I didn't do that, then it would just move wherever, somewhere outside the plot. Okay, so that's one problem. The other problem is, of course, insufficient data. When your simulator is expensive, that means it takes, let's say, hours and hours to do, let's say, one computation. You don't have the luxury of sampling a lot of thetas and then simulating and then doing rejection, whatever. In that case, you're basically doing this regression of these regression adjustment methods with only a few data points, which means that if there is some noise in the statistics, or you have statistics which are not really informative, the regression model is not going to be very accurate. Okay, and so here what I plotted is, again, green denotes the true value. There is 3 different types of regression ABC method. This is when uses a linear model, is a neural network, and this is ridge regression. And so the red one corresponds to when you have a lot of data points. And then the blue one is when you have only a few. And so, as you can see, sometimes there's only a few data points. That's why the posterior looks like this. And it's concentrated sometimes outside, very far away from the true value. But at the same time, it's also very sure that it's there. So that's kind of double problem. Okay. Now, the question that we're asking is, can we mitigate some of these issues by leveraging domain expertise, given that the domain expert is so much involved in this process already? Which brings us to to our method. And any questions at this point? Yes.
Can I just clarify what you mean by moving the samples to the observations?
Moving this.
So if you go back.
Left to right, like you turn in a page.
But I'm going back.
Yes, page.
Okay. Yeah, sorry. Yes.
Yeah.
Okay.
Yeah, what these, so you're moving the samples onto the.
Yeah, so let me go back to here. So what's happening here is once you fit the line, then you adjust your parameter samples using the residuals. So all of these, they kind of, I didn't even touch it. Okay, so you move it, you kind of condition on your observed statistic, and then basically move each of these samples as if they came from SOP. So we are trying to account for the fact that these samples, they are from the joint distribution of theta and S, but what we want is theta given S. So some sort of a kind of conditioning that we are doing based on this regression model. And then exactly this conditioning is what causes problem if there is a model mismatch. Okay.
Can I ask another question? Could you go back to one more? I'm surprised to see that 500 data points is a particularly low data regime. What's the dimensionality of the data?
It's not exactly 500 because 500 is the total number of simulations that we did. But then first you accept certain amount of samples.
Okay.
And if I think you're accepting like 5% or something,
Right. Okay.
then it's like very few samples to do it. That's the only problem. But in principle, you could do it from all the samples itself if you wanted to. Like this regression adjustment, which maybe is slightly better, but yeah. Okay, so now we come to what is called human in the loop ABC. So now we are trying to explicitly involve the domain expert in the inference procedure. Okay, so this is, let's say, the domain expert. This is our method. And what we want is, we know that this guy has some knowledge about the statistics. What is a good statistic? What is a bad statistic? But of course, they don't know what exactly statistics to use for this particular problem. That's why we call it tacit knowledge. So they cannot explicitly write it down. But if you query them appropriately, then they can give some, let's say, educated guess on whether this would work or not. So that's the kind of information or knowledge that we are trying to elicit. So what we do is, let's say they have some notion of, this pool of statistics. We pick one of these statistics, and then we ask them, is this a good statistic to add? And then they'll tell whether, yes, that makes sense, or whether that does not. Then they just give a feedback based on yes or no. And then we incorporate that feedback and then try to find the next best statistic. And then this process goes on till we converge. And that's our method in a nutshell. And here we assume that querying the expert is costly, their time is costly. We don't want to ask every little question. So we want to do it slightly more clever than just, picking one statistic at a time and then asking them. All right. So a little bit of notation now. So let's say you have a pool of statistics S and it has W statistics. And then we introduce a gamma variable, which is a binary variable that tells whether the jth statistic is included or excluded. So 0 exclude, 1 include. Okay. So that means for any set of statistics, any subset of statistics, we have an associated gamma vector, which is 1 for all those chosen statistics and 0 for the rest. All right. And then, so we have, we denote the ABC posterior, which is theta given the data, and this choice of statistic, because the choice of statistic will matter, will give a different ABC posterior. And now let's say gamma star is this desired subset of statistics, which is the perfect trade-off between information loss and cursive dimensionality given your pool. And that is what we want to have. But of course, we don't observe gamma star. But we can ask the expert about what they think gamma is, which basically means whether to include it or exclude it. In this case, there's only two choices. All right. So for that, we need, since the expert is providing some data, we need a model of how that data behaves. So make a probabilistic model of that so that we can include it in the inference. And we need this sequential experimental design, right, to kind of figure out what is the next best question to ask the expert. So these are two kind of elements we need. So first one is this expert feedback. So let's say the expert feedback is Fj. Again, it's information about gamma, so it's binary. The expert is just saying yes or no. And then we model Fj as a noisy version of gamma. Okay, so gamma has some prior, and then given that, given gamma, the F is modeled as a Bernoulli. And now here pi is this level of noise. So if pi is, let's say, 0.9, then 90% of the time, the expert correctly recognizes that the statistic should be added, and then there is some 10% noise. Sometimes they get it wrong. All right. So rho is the prior probability of selecting the statistic. We just assume that every statistic is equally probable to be selected in the beginning. And now let's say F is the set of feedback obtained after k rounds of this game, this iteration. Okay. Now, because it's a simple model, the posterior is available in closed form. So now, going from the ABC posterior given gamma, we now want to get the ABC posterior given the feedback, which is basically just taking expectation over this posterior. Now, none of these quantities, well, apart from here, I mean, they're not tractable, like, for example, this one, but you can get samples from it. So if we sample from this one, and then we sample from that one, we get a sample from the ABC posterior based on the feedback. Okay, so now we have that. Now we can construct our experiment, which is at, let's say, iteration k plus 1. We select the next statistic according to this rule. So we find which statistic in the remaining pool of statistics, if we add them, it leads to the highest amount of change in our posterior. So this is the current posterior at iteration k, what we have gotten. And then we figure out of the remaining statistics, which one should I add? So which feedback should I get such that the improvement in KL is the maximum? So which basically means that on adding which statistic, my posterior is going to change the most. And we assume that that is going to be caused by, informative statistic, because if it's a statistic which does not have much information about theta, it most probably is not going to change the posterior much. Okay, and this scale, of course, it's we estimated using samples, using this one nearest neighbor estimate of KL divergence from here. And then the stopping criteria of this experiment is when our KL divergence does not change, when the posterior barely changes from one iteration to the next. And if this change is less than delta, which is another hyperparameter of the method, then we basically stop. Like, okay, it seems like there's no more informative statistics left. Now we can stop. So, and the output is basically, you have all the statistics that the expert said to include, which the feedback came out to be 1. That And then the rest, so for that, the gamma would be 1, and for the rest, it will be 0. Basically, we don't include any of those. All right. So now, when we do this, before going on to the, yes.
So this might be misunderstanding. Is there a reason you can't just like use all of the statistics every time and sort of evaluate them somehow based on?
You could, I mean, you mean in distance computation?
Just, I don't know. So if you're sort of picking a statistic.
Yes.
Iterative,
yeah,
and doing some evaluation. Could you not just use all the statistics?
For which purpose? For computing, for doing ABC?
Well, not for doing ABC, but to then do some evaluation on them to select. Like, why do you only sort of evaluate in some sense one statistic each time? I don't even know if this makes sense.
I mean, so we don't necessarily evaluate, we pick the statistic which, let's say, we think is the most informative. And that is what we're trying to do here. We're trying to construct some utility of each statistic. And if we think it's the very good statistic to ask or to add, then we ask the expert about it.
Yeah. If,
let's say, we also don't think it's useful, then there's no point asking the expert about it. Right.
I think that's true.
So that's the.
And that's presumably worse than picking and statistics at the beginning based on having no data and just asking the expert about those.
I mean, so if you picked all the n statistics and asked the expert to classify all of them.
No, not all. Like
just the expertless ABC.
No, I thought that question might have been about batching the questions. So sort of at the beginning, instead of picking one maximum, I pick 5 maximum and ask about them.
Oh, you could do that. Yes, yes. And you could also even ask multiple experts about it. But then the feedback is not as, let's say, simple to incorporate anymore. I mean, it might still be doable. Like instead of 1, you could ask for 2 feedback and then somehow incorporate both of them and have a joint distribution of, let's say, F1 and F2. I mean, that could be doable, yes. But this is like literally the most simple model that we could think of.
So just to clarify, so you have a list of statistics.
Yes.
And you'll go into an expert and ask them which they think is the most informative statistic.
Yes.
And then you're using that to calculate your distance.
Yes.
Okay.
Yes, exactly. So after this experiment is done, and then there are some statistics which the expert said yes to, and then the rest which they said no, or which we didn't even ask, or they said no to, we exclude. And those are the ones that we use for ABC down the line.
And what's the reason for getting rid of statistics? Just that they're uninformative, or?
Yeah, so the reason is basically two. For one is the curse of dimensionality. So if you have more statistics and you're doing distances, then you need to, let's say, sample more thetas. So the acceptance rate goes down. So in order to get more accurate distances, let's say for a fixed epsilon tolerance threshold, you would need more evaluations and more samples from the prior to get those. The other reason is exactly if you're adding a lot of useless statistic or uninformative statistic, that just adds noise in the distance computation. So that just makes it less accurate. That's all.
Can I ask another question? Could you go back one slide? Especially in the model misspecification scenario, is it at all possible that a statistic changes the KL a lot, but it's misleading?
Yes, very good. Yes, we'll get to that. Absolutely. So that's one of the let's say drawbacks of these subset selection methods, which because they also rely on some sort of notion of informativeness. But if you're judging that by changing posterior, when the model is misspecified, we saw the posterior can change dramatically. So that would be like the first statistic that we would think of adding, right? So we do handle that case, but that one is slightly different because here we are leveraging domain expertise. So we don't show them anything. We just ask if this is a good statistic, and based on your domain knowledge, you judge. But for that, we will do slightly differently. We'll show them something and then ask whether this should be added or not. Okay. So this is the low simulation regime case. So we took this G and K distribution. It has 4 parameters. It's a univariate distribution. And then we took 15 statistics. Now, 4 statistics are in the literature. They are known to be informative about those 4 parameters. Then we added 6 more of, just multiplying these statistics, one by one to each other in pairs of 2. And then we added just 5 noisy statistics, which is just some random noise that we added. Okay. And then now for different budget, we evaluate the different methods. So all the regression ABC methods. And this particular method, which is called Barnes, that one is our method minus the expert. So if you did exactly this subset selection thing sequentially, but you did not ask expert anything, what would happen then? So what we see is, and now here is we compute, let's say, the distance between let's say, some reference posterior, which we calculated using a lot of samples, and let's say the posterior is given by these methods. And so the lower, the better. And what we see is that when the simulation budget is low, we perform better. And then after a while, let's say the linear ABC kind of catches up here, and the other methods also perform fairly okay. So it's the advantage is exactly when the number of data points is low. Okay. Now, so what's happening here is, even though the data point is low, we have some extra information that the other methods don't have. So with low data, now you're trying to compute, estimate your KL divergence, all your posteriors and blah, blah, blah. But all of these are going to be very noisy because you're just computing these from very few samples. So you could, erroneously think that, oh, this particular statistic is informative, but that could just be random noise that is, telling you that, oh, the posterior has changed. What's happening in our case is that the expert kind of balances or counterbalances, whenever we are wrong. And this is what we see here. So now this is the number of questions that we ask the experts, the number of times we, queried expert feedback. As the simulation budget increases, we saw that we need to ask less and less questions. And after some time, basically, you don't, even if you don't need the expert, you'll perform fairly well, right? It's only when we have few data, then we need to ask, let's say, a bit more questions. And here, this is just a random acquisition scheme. So instead of doing this sequential sampling, sequential experimental design, just to show that, we are trying to be optimum in the sense of reducing the number of questions that we ask. Okay.
I'm sorry.
Yes.
In random, you're still asking a human.
Yes. But it just, we are picking randomly from this pool of statistics rather than doing our experiment. Okay. I think that's all that I wanted to talk about this one. And now comes the model misspecification. Now, we are not asking them whether this is a good statistic. We show them what happens when a statistic was added. And here, this expert, for example, the one that we did the experiment with, they are familiar with the problems that the regression ABC, has. So the fact that, posterior can move, if they don't know, then of course, but I mean, even if you don't know, that looks very wrong, right? So here we took like a radio propagation model, which is a high dimensional complex value time series, but then we compute some statistics, which is shown to be working well in the literature. And now here, expert is shown the inference results and then can detect if, statistic is causing problems. So now it has 3 parameters, G0, T, and lambda. And then this zeta signifies the misspecification level. So a little bit misspecified, more misspecified. Then we see that, okay, this one is the posterior and the yellow one is the prior. So the prior is, of course, uniform, flat. When we added the misspecified statistics, so, okay, I didn't explain that one. So there's 6 statistics. One of them, we artificially make it, different than what the model gives. So we add some noise onto one of them in the observed data, but for the simulator, we don't do anything. So what happens here is that, as you can see, for these two, the posterior gets shifted, as we saw the behavior with in the beginning, towards one of the prior boundaries. If you increase the misspecification level, this just becomes more prominent. And so what our expert is basically doing is whenever they see this kind of behavior, they say, no, don't add it. Even though in the well-specified case, it is an important statistic, but let's not add it. Just by doing that, we see that, I mean, things improve much better. So here is the well-specified case. There's no zeta. And both the methods are the same because we're using the same statistic. We're using the same ABC method. Okay. And, the expert has no issues here. Here, when there is some misspecification, now the posterior for T is exactly on one of the prior boundaries, same with lambda. And that one also looks quite wrong. But then if you just exclude it, from the 6 statistic, you go to 5 by just removing it, you get, again, back to what you were. Of course, there's some degradation, but that's what you would maybe expect. So yeah, that's about it. And with the expert in the inference procedure, we have, let's say, the luxury to actually be able to detect it, during the fitting procedure. That basically brings us to the end. The concluding remarks are that we introduced the first ABC method that actively leverages domain expertise in order to do this statistic selection. And we saw that with fairly limited effort from the expert, which is answering a few yes or no questions, we are able to even handle cases which, let's say, existing methods could not, which is, misspecification, low simulation regime, and so on. Yeah, and that's about it. And now, of course, this is the more machine learning side of it, but you could also think of this method as some sort of an AI assistant. So let's say you're an expert and you want to fit your model, and you just pick all the statistics from the literature. You don't know which one is going to work, which one is going to not. But now you just feed into the, let's say, the algorithm, and then one by one, there you get to ask. So the algorithm asks whether this is a good statistic, and then maybe even if you want to see the inference results, you can do that, and so on, and then converge to, let's say, a good subset. So it kind of the motivation for this work started from reducing the domain experts' work, so that they don't have to do everything manually and handcraft statistics. Maybe we can try to automate this process. But then, of course, that's not a machine learning paper unless you solve some machine learning challenges. So, but turns out we can also solve some challenges with this. That's the end. And yeah, questions? You can clap first, and then we can. Yes.
I might misunderstand a bit. So, if the selection of the statistics is mainly based on the experts, so what does that maximizing the KL divergence go?
So that is for us, for the AI to figure out which is a good statistic, to ask the expert. So that's like the first step that we do. So we don't want to ask about every statistic. We want to first figure out what is a good statistic to ask. And that is the KL is for. So if to find some informative statistic, and then we ask the expert whether this is a good statistic to add. And of course, if you have enough data, maybe the expert's opinion does not matter much, unless, of course, you're in the misspecified scenario. But if you have low data, we could be wrong, right? But we don't want to ask about every question. This is to limit the amount of feedback the expert has to give. That's why we're trying to do this experimental design first.
So what would happen if you just remove the KL, just refer to experts every time you choose a statistic?
So if, let's say, you're saying, well, then the expert is doing everything on their own, like basically checking one by, how would you check whether a statistic is good or not then?
Just rely on the experts?
You mean just ask, but that's the starting point, that the expert inherently don't know whether a statistic is good or not. But if you query them appropriately, they might tell you their domain, what is their latent domain knowledge. So I see your point that, okay, if the expert is doing it, then let the expert do everything. But we are trying to help the expert in solving some of the issues. Yeah. Yes. Yeah, go ahead.
It seemed like when you're choosing the statistics, you're doing some sort of like greedy
yes
choice.
Yes.
Have you looked at like other possible choosing or selection methods?
Yeah, I mean, so what we're doing is this forward subset selection, which is one by one. Of course, that may not be the most optimal, but we didn't look at others because they're more computationally expensive. And anyway, with the simulators and ABC steps and all of these things, it is quite computationally expensive already. So yeah, we might not converge to the best subset of statistics for sure. I mean, that might happen, but we hope for the best. You were saying something? No.
Question about asking experts about misspecification. Is there a way to detect it without asking the expert? Because if you show an expert that plot, like I feel like there should be something that tells you something's wrong with the plot.
So
yes,
it's very detecting misspecification. Actually. So the behavior of this particular ABC method has been proposed also by us to use it as a way to check if your model is misspecified or not. But that, of course, involves that you do the inference and fitting, and then the posterior that you get. And if it is completely rubbish, then you're like, okay, maybe the model is not, specified. There are other ways to check it. There's not a lot of work in this, and my colleague and I were trying to look into this, but you can determine it from the summary statistics space itself. So I don't know if I have any figure here. So imagine, let's say you simulated a lot of theta from the prior, and then you ran the model, and then you have a bunch of statistics. Okay. If you plot those statistics, if let's say it's just 2-dimensional, and then you plot a scatter plot, then they'll form some sort of a point cloud, which kind of tells you, the kind of statistics that the model can generate. Now, whenever the model is misspecified, and then you observe some, let's say, observed statistics, this thing will happen whenever the observed statistics is outside this point cloud. So you could detect it, some sort of an out of distribution detection exactly there, instead of running the inference and then guessing that, okay, it might be misspecification. Now, the trick, not the trick, but like there is a little bit of caveat here that your model could be misspecified. So your data does not capture, your model does not capture everything that the data is doing. But since you're only looking at statistics, which is a low dimensional representation, it might not be misspecified there. So the misspecification of the model is lost in some statistics, which let's say we didn't even include. In that case, you won't be able to detect it. But whatever little misspecification people have looked at, it's always in these cases where, of course, you can, when the summary statistics kind of lead to this kind of a problem. So some sort of an out of distribution effect is what happens. Yeah.
Are you able to learn your statistics?
Are you able to learn your statistics? Yes. So a lot of work. So there has been papers on just learning a good representation of your data. So you of course, then you use a neural network. You use you feed in your data, maybe use an autoencoder or.
I was going to say, because the like statistics and finding this is a bit like a encoder discriminator type.
Yeah, exactly. So either you can use the encoder layer as a statistic, or you could train, let's say, in a supervised manner, so the parameters and the statistics. So sorry, the data and the corresponding parameters, and then you take the estimate of the parameters as your statistic. So then you have one statistic for each parameter. You could do that. I mean, there are pros and cons for both approach. The con is that you're losing sense of what you're trying to fit. And it's not, I mean, when you do in practice, it's not really always very straightforward. Oh, pick a state of like run-of-the-mill neural network and then outcomes. You need some work in order to fit it properly. But on the other hand, you don't have to do all this handcrafting of statistics. So pick your battles.
Presumably in a low data regime, and autoencoder should not be.
Yeah, exactly. So yeah, so any neural network type of method with a low data regime is not going to work very well anyway. So
do you think, and I don't know what these statistics look like, but do you think it's feasible to to define some metric on them and introduce relationship between statistics. So now we model statistics as just as purely separate like
Yeah,
entities.
yeah.
Is it feasible to introduce a relationship between them? And so the probabilistic model on statistics too.
To do what?
So like if I know that statistic A is close in some sense to statistic B, then
I mean, like they're correlated.
yeah, for instance,
Then
then what?
I mean, then you could. I mean, if they are very correlated, then maybe it doesn't make sense to include both of them.
Okay, so
I mean,
that happens at the pre.
But I mean, I don't know how much that would affect in practice, as long as they are correlated, but they are also informative about the parameters. It should be fine.
Sure.
Yeah. Maybe so. There's one case which I cannot maybe draw here, but think of again S1, S2, two statistics, and then you're plotting, let's say, the scatter plot, and it looks very correlated, like a very correlated Gaussian contour. Imagine something like that. Now, your observed statistic, if I plot there, it might be outside this, let's say, oval shape, but it might still be within the range for each of these statistics. It's a bit difficult to imagine, but like if now the Zoom people are lost at this point, but like imagine that
They can see a video.
Okay. Well, I don't think that'll help. But like if imagine like a very correlated contour of statistics, two statistics that I plotted, and then the observed one for the same lie outside this contour. But if you look at the marginals, it would lie somewhere in the middle of each of those marginals. Then you would run into problem. Then you wouldn't be able to detect it. But if you're kind of fitting it together, you might still run into the same problems, but looking at their marginals are not going to help you in that case. But
that's closer to the greedy question, I suppose, that you asked.
Yeah. But I don't know. So that particular problem, I've been thinking of, like a simulator or a practical case of how I can generate such a misspecification, so to speak. But it's a bit difficult to make that case happen. I don't know how often that happens. Yeah. All right, that's. I think I learned in the end how to which way it is. Okay, and no questions from the chat.
No. If anyone, if anyone on Zoom has questions, then also feel free to unmute yourself and just ask them.